So good evening. Thanks. I am Devmalla Chakraborty. I am from IIT Kharagpur. So I will be talking on something which is unconventional superconductivity and unconventional magnetism and how do they compete. So first of all, I would like to thank the organizers for giving me this opportunity, and especially I'm lucky to speak. Being one theorist in the whole session, I feel to be lucky, and I hope I don't empty the room more. So basically, whatever I will be talking on will be based on these references, and all the works are done in collaboration with Annika Blackschaffer from Uppsala University. And in the next 20 to 30 minutes, we will try to see these phase diagram many times, what happens in magnetic field and altermagnetism, which looks something like this. How many of you have seen this figure before? Oh, very few, because of the generation gap. I have never seen this 3 years back. This is Yoda from Star Wars, and if you just look at 1 year, the phase diagram looks like one half of the year, 1 year. So that's it. So before getting into the phase diagram, let me talk about some familiar magnetism that we know. As Professor Singh has already mentioned many things, so my job would be easier. So we know about ferromagnetism, where spins align in the same direction. Like, let's say if it is down, all the spins are down. And if it is a metal, the Fermi surface would look like this. That means the down spin will have a Fermi surface like the blue one, let's say, and the up spin will have a different Fermi surface. So there will be a spin splitting between the Fermi surface. The other form that we know is the anti-ferromagnetism, which is like up, down, up, down. If it is this is shown for a square lattice, so we can have down, up like this. If you look at the Fermi surface, however, up and down are degenerate. So there is no difference between up and down. There is no spin splitting. So there are some gaps because of the Q vector in the antiferromagnetism, but both spin up and down are same. More recently, what we have been talking about is something called altermagnetism. Specifically, I am showing one particular form of altermagnetism, which is a D-wave altermagnet, where it's not only an antiferromagnet, that means it has an up down configuration if you look at the spins, but additionally if you look at the structure, there is an additional structure to it. That means either due to crystal field splitting, or so you actually introduce a sublattice which is no longer there in here. Here we have a spin sublattice, but if you just translate and rotate, you get back the same thing. However, if you translate but rotate, you will not get the same thing. So basically what happens, if you look at the Fermi surface, the yellow one, let's say the up spin, and the blue one, which is the down spin, will be split, and this splitting is the strength of the magnetization. And if you look at the magnetization throughout the Brillouin zone, it would be positive and negative. So the net magnetization will be 0. So there is no net magnetization in the system. It will be sign changing, and there are points which are like these green dashed lines, these points which are like the nodal points where up and down are the same Fermi surface. That means they are degenerate. Before going on further, so there is a nomenclature that I want to set. So what I will be saying, unconventional magnetism, is that all magnetism that is where the magnetization is momentum dependent. That means when I am talking about this is a D wave, dx square y square magnetism, and typically in the community it is used that unconventional means non-collinear p wave ones. So usually the D wave altermagnets are not called unconventional, but I will call them unconventional in the spirit that they have a momentum dependent magnetization. So if we look, as Professor Singh already mentioned, that superconductivity and magnetism, they don't like each other. That is not always true. So they have a friend-foe relation. So if you look at typical phase diagrams, there would be these competition. If you look at antiferromagnetism, there are very small coexistence places. So there are places in some iron based and heavy fermion superconductors you can get coexistence. You can also have a phenomena that near a quantum critical point of antiferromagnet you can get a superconducting dome. That means due to the fluctuations of antiferromagnetic quantum critical point you can get superconductivity. Similarly, if you think of ferromagnetism, that means which are all down or all up, near the quantum critical point you can again have some fluctuation induced superconductivity, which usually are triplet because it's all up or down. Again, we still have some materials which are believed to have some coexistence, like some heavy fermions, again because like UG2, these they have some coexistence. There are some weird niobium diselenide actually treated with molecular surface absorbance can show a coexistence. It was a paper 10 years back. So there are some example of coexistence. So you again get a friend-foe relationship. Now what happens with in the presence of spin splitting, you can get, as again Professor Singh mentioned, you can get something called finite momentum superconductivity. So let me again mention it, that usual BCS Cooper pairs are made of k up and minus k down. That means let's say if this is a spin degenerate Fermi surface, this is a k up. So if I want to pair this with another electron minus k down, I will have one here. Now if the spin Fermi surfaces are split, that means this is the up one and this is the down one. If I want to find a minus k down, I will not find one, because this YOLO is only the up spin. So as a result, the equal energy point would be somewhere shifted, which would be minus k minus q. While in this case, the usual BCS case, we get the center of mass momentum, that is k plus minus q is 0. Here the net momentum is q or minus q. That means that's why we call it finite momentum superconductivity. So this was long known that if you increase the spin splitting, then you get from 0 momentum BCS state to a finite momentum state to a normal state eventually. This again, as Professor Singh mentioned in the last talk, 1964 Fulde-Ferrell and Larkin-Ovsyannikov. I just want to add one thing, that Fulde-Ferrell said that the order parameter will have a finite q, but this will have an exponential, it's a complex with q dot r, it's a changing complex phase. However, LO, which is Larkin-Ovsyannikov, this has a real order parameter which modulates. More recently, what happened 8 years ago, that they came in a new avatar which is called a pair density wave, where we do not have any spin splitting, but they still show some modulating superconductivity. They are seen in many compounds now, cuprates, TMDs, Kagome metals, iron based superconductors, and many other actually in heavy fermions. So with this new adventure, we actually can ask the question within the alter magnet which has these structure. Let's say if we consider the D wave alter magnet, it has sign changing magnetization, nodal points. Can we get finite momentum superconductivity with this structure? So that was our original question. So to solve this question, what we did is to start with the mean field Hamiltonian. We have a normal state, we have this pairing term which is given by delta q, and this normal state has a sigma times TAM. This TAM means this is the strength of the spin splitting. So if I have larger TM, my spin splitting would be larger, more alternatism, and we take it to be dx square y square, and then add superconductivity. So we solve it self-consistently using a Bogoliubov-Digens theory, and we treat q variationally. That means we check the free energy as a function of q and take the minimum q result. So what we start with is to start with the superconducting order parameter, which is constant in momentum space, S wave. So if it is S wave, we try to change TAM and try to see if we can find finite momentum superconductivity. So to our disappointment, if we keep on increasing this TAM, which was the alternatism strength, we get from 0 momentum to a normal state, there is no no finite momentum superconductivity if you take a S-phase superconductor. The reason is very simple. So if you look at the pair density, that means expectation of C dagger. So if you remember the structure of the altermagnet, it had nodes. So if you look, if it is visible, there are 4 nodes. If you look at the pair density, you still have some pairing left at those nodes because those are degenerate points. As a result, the condensation energy gained due to the BCS zero momentum pairs, they win over forming a finite momentum pairing. Now if we consider a D wave with the same symmetry as the altermagnetism, that is dx square y square, then what we see is that we can actually get a finite momentum superconductivity without any magnetic field with no magnetization. So we get a region of TAM where we get a finite momentum superconductivity, and then eventually if you increase TAM, it will go to normal state. Now if we want to actually look at the effect of Zeeman field, so now when I am talking about magnetic field, in contrast to what has been talked about in the two talks before, these are not the vortices, these are just the spins effect. I am just looking at the Zeeman effect of magnetic field. So with the same Hamiltonian, I just add sigma b, where b is the magnetic field. Now I want to look at the phase diagram, and then the phase diagram looks like this. So if TAM, this is TAM axis, which is the altermagnet strength. So we know this axis from long before, that if there was no altermagnetism, we go from BCS to finite momentum full de state to normal. I showed you just before there was one axis which is at zero magnetic field, you go from BCS to finite momentum to normal. Now if you have both of them, you get this Yoda here, where interestingly we get a field induced superconductivity. That means if you have a material which has an altermagnetic strength somewhere here, you give a Zeeman field and you induce superconductivity. Why is this happening? So if you look at the Fermi surface at this point, let's say if at this point, this was the spin split Fermi surface that I showed you earlier. So these were the nodes, these are the maximum spin splitting. Now if you keep on increasing the magnetic field, Zeeman field, these nodes actually go closer to this point, kx equal to 0 point. If you keep on increasing near this region, what happens, the nodes, they coincide and they go to the antinodal region of the superconductor. So a D wave superconductor has maximum pairing here, and that is the region where it has a degeneracy. And as a result, if you look at again the pair density, you see that at this region you gain superconducting condensation energy, and as a result you start forming superconductivity, and then eventually you will gap that, there will be no nodes. Now how much time do I have? I think 10, 15.
Yeah, about 15.
Okay. Yeah, so this was that we wanted to understand what happens. So the finite momentum superconductivity, or the FF state in an altermagnet, also has very significant application in superconducting diode effect. Again, Professor Singh mentioned that. So what we know usually from long ages back, we know diodes have this property that you have electricity in one direction, no electricity in the other direction up to a particular volt. So this is the usual diode semiconductor PN junctions. Now more recently there are these superconducting diodes that are proposed, which means that, so there is this critical current in the forward direction which is not equal to the critical current in the reverse direction. So that means the critical currents are non-reciprocal, and the diode efficiency is actually calculated typically by taking the difference between the IC plus, that means the forward critical current, minus the reverse critical current, and you normalize it by its average. Now to look at the diode efficiency in the same case that we have calculated, so we look at the same phase diagram, but the color now indicates something else. The color is the diode efficiency IC plus minus IC minus by the average, and if you look at the efficiency, it is only there, that means the superconducting diode effect is there only if you have finite momentum superconductivity, because this FF state actually breaks the inversion and time reversal both. As a result, you will have this diode effect, And if you see and look at the efficiency, these are multiplied by 10, 100 to get the efficiency. You get efficiency of order of 60% to almost 100%. That means if you look at these regions, these are almost 60% efficiency. And interestingly, you see that these regions have almost perfect efficiency. By perfect efficiency, I mean that you have a diode efficiency of almost 100%. And this is not miracle. What happens is that this is a common feature that can be seen near BCS to FF transition if it is a second order. That means, so the critical current is actually a derivative of the free energy with respect to Q. Now if I plot the free energy as a function of Q, which is the Cooper pair momentum, if you look at the free energy, it has a minima near some Q value. That means I have a finite momentum superconductivity. Now at this point, if I do a derivative, the critical current has to be 0 at the equilibrium. Now if I look at a plus Q and a minus Q, that means in this direction and in this direction, you can already see that the slope in this direction is very flat and it's quite steep in the other direction. That means if I look at the derivative, which is the critical current, will be very low in one direction and very high in the other direction. That means if I do the look at the efficiency, it will be very high. And this is happening because the Q equal to 0 has a very weak minima and energetically they are very similar. Near this transition, they actually cross and they become equivalent, and as a result it's a flat thing. It's much more interesting because it's not all BCS to FF. That means if you look at this BCS to FF, it's not perfect. The efficiency would be 20 to 30%. Efficiency will only be perfect if you are near a second order transition, and that happens because, as I said earlier, that this structure with magnetic field actually goes from nodal to nodeless. So there is a topological transition of the Fermi surface. That means it goes from this 4 nodes to no nodes, and this blue line actually indicates the transition from nodal to nodeless. And if you look at basically these red points are the points where efficiency is extremely high, you see that they actually lie on this line. So it will be high here and here. Now till now what I have been saying is that I take S wave, I get this, I take D wave, I get this. But can we actually say something that if we have altermagnetism, can we say what would be the superconductivity that is possible in an altermagnet? To understand that, we have to go deeper rather than just looking at this model. So to understand why we get this spin splitting, we have to go back to basics. So first we have to consider 2 sublattice and 2 spins. So I consider a basis which is AB 2 sublattice and up and down 2 spins. That means there would be 4 cross 4 matrix, 4 bands. Let me consider a square lattice. Then you will have some dispersion which is like this, and they will be all degenerate. So if you look at all the bands, they will all be degenerate. All A, B's are degenerate, all up, down are degenerate. Now let me introduce a term which is like TM but some other TM, where I introduce sigma which is spin and tau which is sublattice, a tau z in the sublattice. That means I break the sublattice symmetry between A and B. Still I do have spin degeneracy, so I get this band structure. Now additionally, if I put a sigma z and tau z, that means another exchange interaction, I see that there are 4 bands, and at the low energy at 0 near the Fermi level, I have this Fermi surface, and effectively what I can consider is a 2-band model. This is the TM that I have been showing some slides back. But what we have to keep in mind is that these 2 low energy bands are not just up down, they are coupled with the sublattice. That means A has up and B has down. So that is spin sublattice locking that we cannot get rid of, and as a result, if you look at the pairing possibilities that can come up are very restricted. That means if we think of S wave, that I was saying that okay, by hand let's say we have S wave, we cannot, because S wave would need on-site up-down pairing. There is no down band near this A side. Similarly, there is no up band near B side. So this spin singlet S wave pairing is not allowed at all. think of triplet, equal spin triplet, that would mean that there is a p wave pairing, nearest neighbor p wave, which is this case, and that would need up in nearest neighbor, which again cannot happen. As a result, it's so basically this constraint that the spin and sublattice is locked gives rise to a fact that many of the pairing cannot happen. And as I was saying, the D wave is one of the highly likely possibilities, which actually we derive to show. So till now I was assuming that there is alternatism. Now I want to get alternatism from interactions. So I take a lattice which actually was proposed in this paper. So we take this lattice with T1 not equal to T2, that means the hopping in X and Y are asymmetric, which breaks the rotational symmetry, and we put a Hubbard interaction, do a mean field, and what we get is to, if we look at the staggered magnetization, the M, as a function of U, the Hubbard repulsive interaction, you see that if you keep on increasing U, you start getting M, and there would be some magnetism, and that if you look at the Fermi surface, you will see that it's spin split, that means it's an altermagnet. And if you look at the sublattice contribution of these individual spins, you will see that this up spin is actually fully apolarized. You can actually calculate it. You can also calculate the B sublattice weight, and it will be actually polarized for the up spin, sorry, for the down spin. And now if we add pairing, we can see that S wave actually goes away as soon as we have M coming up from this Hubbard repulsion. So if we, as soon as M comes up, S wave becomes 0, there is no possibility. But if we allow for D wave, we will see that there is a finite momentum pairing coming up near the transition. Now to summarize, I think I am on time. So basically we got this phase diagram and different properties. We also have looked at some properties of Strongsheim-Ruth net, which I am not going to mention as I didn't mention in the talk, which we did with Carmen, who is doing the density functional theory calculation of Strongsheim-Ruth net. But at the model level, what we saw that the phase diagrams can be very interesting if you have alternatism. And to end with, I would like to thank you and also advertise that we at IIT KGP, we are a group which we call Top Disco, which is topology and disorder in superconductors and other correlated matters. So if you want to know more, sorry for the people sitting here, I don't think you will be able to see the QR code, but the QR code has a website which you can see, and we are looking for project masters, PhD and postdocs, so just feel free to contact me. Thank you.
Thank you, Rupal, for very interesting talk. So the session is open for questions. Satyajit.
So I was curious to know, how did the gap, the degeneracy in the altermagnet at those points disappear or go away with the applied field, that when you applied the field they actually went away, they became gapless?
So if you look at the dispersion basically, so if you look at the dispersion of the two band model itself, first of all you will see that this dispersion, if you add, they will go away at some points. So if you look at, just plot this, what will happen is that there is a XY asymmetry that will come in.
Momentum is just gapping out that.
It will just gap out and move it towards the other point, and beyond the critical field it will become fully gapped. In plane, just a sigma z term.
One small question is that, of course, this is in momentum space, and some experiments on FFLO have seen that there are these order parameters which actually cuts along the field direction. It becomes 0 along as you apply the field in this. There are nodes in the Q, the cos Q term. So that cos, that zeroing out the Q, what determines that? I mean,
so if we, in real space you are saying, so basically if we have both Q and minus Q, then we will have a LO state which will have a cosine that will have zeros in the order parameter.
What determines the wave
So ideally the Q from this to this. So if it is in the simplest picture, it would be this spacing in the this spacing. So the Q changes if you change the splitting. Yeah.
Hi, so I have one query. Let me first. So here, what you are saying is in ultramagnet, no P-wave superconductor conductivity.
Equal spin triplet P wave. You can have mixed spin P wave.
Okay, mixed spin is.
Yeah.
And second is you are talking about the increasing ultramagnetic coupling. So you require a large spin splitting, because that point I really got confused, because your finite momentum pairing state is only existing when you have TM very large, right? More than like.
No, not large, but actually weak, I would say, rather, because if this is the region where I have, if you most seen materials are, this is quite weak compared to them. They are like one.
Yeah, that's
times.
exactly I am coming. So which material is suitable for?
So actually, first of all, the first thing that we need is a metal. First thing. So this new material, which is this potassium, vanadium, selenium oxide, that is a metal at room temperature. Unfortunately, the magnetism is quite strong there. So I do not expect to get superconductivity there. There are other variants of that which has one interesting material which is under, there are two materials which are under controversy. One, ruthenium dioxide, which is
that is magnetism itself
is controversial, but you actually get superconductivity in the strained ruthenium oxide. Another one which is very interesting is iron selenide, FeSe. If you look at the monolayer, you can have ultramagnetism. Actually, they have seen finite momentum superconductivity in FeSe monolayer. So that, if looked at carefully, is the place where it can, these can be applicable.
Any more questions? Yeah.
Just a quick question,
Yeah.
maybe I missed. So in this diode part,
Yeah.
this is a two-band model, right? So it's already pseudo spin.
Yes, but
Is it
this,
usual VCS?
what do you mean by usual?
I mean, this is a pseudo spin, right? Yeah, it's a two-band model. Maybe
It's pseudo spin means its spin sublattice locked.
Yeah.
So it's basically when I'm writing this two-band model.
Yeah, the first part when you.
Yeah, so when I'm writing this, I have this.
Yeah, so when the first part you are showing the VCS.
So I can do the same with the four-band model, is the same. Because it is the same. As long as I mimic my four-band model to match the two-band model, that's it.
It's the same.
Yeah.
Okay, thanks.
Hi, sir. So in the phase diagram, the Yoda picture, so in that I have seen FF and FF prime. So
Yes. So actually there are two Q vectors. So that's why I didn't go into detail. So basically this has a particular Q vector. Suddenly there is another Q vector that comes in. So when I was showing you the free energy, I can actually show you quickly. Yeah. So basically there are two minimas. One goes to another.
Okay.
So that's why it's FF prime.
Local and global kind.
Yes. Yeah.
Thank you.
Okay, so the last question is very bad.
In your reagent superconductivity,
Yeah.
what does demand? Like how strong it is?
So actually yes. So what I showed in the beginning had so I didn't tell you what interaction strength I took. I took a larger one to show it realistic. But if I take realistic one, so you can actually get, so if I calculate for not realistic but some value for which are true for cuprates, let's say, I can get a value of like 16 Tesla. But you can go to low. So basically the interaction strength will decide how low, what would be the, yeah.
Okay, thank you.
Okay, so if there is no more question, let us thank Vedmala once again. And